Now we have seen what are fundamental derived physical quantities and how they write their dimensions. We have seen how we can verify an equation using dimensions. Here we're going to try and use dimensions to identify the nature of variation. That's how we've ended our last video. We stated that we can do this. How can we do this? Let us consider an experiment. The variables of an experiment are force, speed, and radius. Details of the experiment are not of significance now. The constant in the physical quantities, constant physical quantities in this experiment is mass. That means mass does feature in this experiment, but we are not changing it. So whatever it might be, we want to find a relationship between the variables and the constants and everything in this experiment. We get some data, and possibly we have a reasonable understanding of what is increasing and what is decreasing. However, we do not know what exact exponents must be there on each one of them. In this particular case, let us say the dependent variable is speed. So we are going to get the dimensions of a combination of all the force, radius, and mass must add up to a dimension of speed. Or not add up, say multiply, or you should not use the word add up, join together to make the speed. Now let us say what are the quantities here. Radius, we know the dimension to be L raised to 1. Speed, L raised to 1 over T raised to 1. Mass, M raised to 1. Force, how do I write the dimensions? We always return back to our equations in order to decide that. We know that F is equal to mass times acceleration, or even if it is K times mass times acceleration, it doesn't matter. So in which case, force must be of dimension mass times acceleration. In our previous video, we saw that acceleration has got a dimension L raised to 1 divided by T raised to 2. Therefore, we know this must be dimension of F must be dimension of M times raised to 1 times dimension of A raised to 1, and that is why we write this as M raised to 1, L raised to 1 divided by T raised to 2. Now we have established these things. Now, if the dependent variable is speed, let us say our relationship looks like this. Speed is given as K, which is a constant, times force raised to P, radius raised to Q, and mass raised to R. Is this, not R, let's call it as S, because R can be radius and confusing. But now, we do not know whether this is the only term we will have. We have more addends there, but we will not have. We know that these are the multiplicative terms that we can have. That means the dimensionality of speed, and since K does not have a dimension, must be equal to dimensionality of force raised to P times dimensionality of radius raised to Q times dimensionality of mass raised to S. So dimensionality of speed we know is L raised to 1 divided by T raised to 1. We know dimensionality of force is M raised to 1, L raised to 1 divided by T raised to 2. However, the whole quantity is going to be raised to P. The dimensionality of radius is L raised to 1. However, the whole quantity will be raised to the power Q. And dimensionality of mass is m raised to 1, sorry, and the whole thing will be raised to s. So let us try to see how the right hand side would look like after we combine all these powers. A little bit of algebra will tell us. M raised to 1 raised to p will be m raised to p. And then let us look for other m terms. There is m raised to s, m raised to 1 raised to s. So that will give me m raised to s. And let's look at the L terms. We have L raised to 1 raised to p will become L raised to p. The other L term we have L raised to 1 raised to q will become L raised to q. And the only term in t we have is here, which is t raised to 2 raised to, the whole thing is raised to p in the top, so it will be 2 raised to 2p. A little bit of simplification will tell us it will be m raised to p plus s, L raised to p plus q, and t raised to 2p. All of that must be of the same dimension as L raised to 1, t raised to 1. We can immediately see there's one quantity which we can immediately find out, which is p. Why? The powers of m, l, and t on both sides must be the same. So let us equate the indices of t. If you equating the indices of t, we have on the left hand side it is t raised to 1, which is negative 1. On the right hand side it is 2p, which is the denominator. Why did I write negative 1? Denominator 1 would mean of power of index negative 1, and this will be negative 2p. So the negative sign cancels off, and this implies p is equal to 1/2. If I equate, is there anything called mass on the left hand side? No. In which case, equating indices of m gives you 0 equal to p plus s. But we know p to be equal to half. If p is equal to half, this must imply 0 is equal to half plus s, and which implies s is equal to negative 1/2. Now, now that we know s, and we also know what is p plus q should be, equating indices of L, on the left hand side it is 1, which is there. On the right hand side it is p plus q, which is there, which is 1 is equal to p plus q. We know p is equal to 1/2, so 1 is equal to 1/2 plus q, which means q must be equal to 1/2. This would mean that this whole thing would become, going back to the same thing, let us rewrite the equation of speed is equal to k times force raised to s. So speed must be equal to k times force raised to p. What is p? 1/2. Radius raised to q. So radius raised to q, which is 1/2. And mass raised to s. So mass raised to negative 1/2. So let me put some notations here so that it's easy for me to read. So I say v must be equal to v is speed, k times f, I'll write for this thing, that is radical f, r, which will be equal to radical r raised to half, mass raised to negative 1/2, I will write that in the denominator as radical mass, the m, which means I can square all sides, and I will not, that means v squared is equal to, I'm going to write k squared to be a new constant. I'm going to, k squared is equal to new constant, let us say n. So n times f times m, r times divided by m. So we do not know what this is, but we know one thing. V must be proportional to radical f, and V must be directly varying as radical r. And we should know if there was a mass which is not constant, V will be inversely proportional to m. So can we write an equation for this? Maybe. Maybe we can write m times v squared over r is some constant times force. That's interesting. So when we get the data, if we all that we can say that v increases as f increases, we can possibly, and we are not very clear about the exact exponent there, because here we use indices and exponents we equated. Because we do not know the exponent, we can try and fit a power regression and see if that exponent comes out to be nearly 1/2. Similarly, if v increases and r increases, and if we are able to say that the power regression between v and r gives you an exponent of 1/2 over for r, then we are reasonably in the ballpark of showing that the experiment is good enough. And however, the physics is the physics. The equations are not going to change in terms of the power, the exponent of f, r, and m are not going to change. However, our data may not be really good enough and may not give you the exact exponents in the best fit graphs.